If you could zoom all the way out of the solar system, past Jupiter, past Pluto, past the Kuiper Belt, you'd eventually hit a region where the sun is just another bright star in a black ocean. And yet out there, space around us is packed with icy bullets that can be kicked inward and turned into world-changing comets. That invisible shell of frozen shrapnel is called the Oort Cloud. And whether you realize it or not, we all live deep inside its cosmic minefield. Here's the weird part. No one has ever actually seen the Oort Cloud directly. We can't point a telescope at it and snap a picture. It's too far, too dark, and the objects inside it are too small. But we're pretty sure it's there because of what keeps falling out of it. Long-period comets that come screaming into the inner solar system on gigantic, stretched-out orbits that take thousands or even millions of years to complete. When you see a bright, icy comet with a tail stretching across the sky, there's a good chance that thing spent most of its life way out in this distant halo, barely bound to the sun at all. To understand why this minefield exists, you've got to roll the clock back 4.6 billion years to the chaos of the early solar system. Back then, our corner of space wasn't a neat family of planets. It was a violent construction zone. The giant planets, Jupiter, Saturn, Uranus, Neptune, were throwing their weight around, slingshotting smaller icy bodies in every direction like pinballs. Some of those chunks crashed into planets. Some fell into the sun. Some got ejected entirely and flew off into interstellar space. And some got just the right gravitational kick to be flung very far away, but not quite fast enough to escape the sun forever. Those are the ones that ended up populating the Oort Cloud. So what actually is this thing? Imagine the solar system as a target. The sun is the bullseye. The planets are rings near the center. Beyond Neptune, around 30 astronomical units away, you have the Kuiper Belt, that donut of icy objects like Pluto orbiting roughly in the same flat plane as the planets. Keep going. At a few thousand astronomical units out, 2,000, 5,000, maybe more, you hit the inner edge of the Oort Cloud. And then it just keeps going. The outer boundary might stretch to 50,000, 75,000, even 100,000 astronomical units from the sun. At that distance, you're already a big fraction of the way to the next star. And unlike the flat Kuiper Belt, the Oort Cloud is thought to be a giant sphere surrounding everything. The sun, the planets, the asteroid belt, the Kuiper Belt. All of it wrapped in a vast bubble of icy debris. If you could see it from far away, our solar system wouldn't look like a thin, flat disk. It would look like a tiny glowing dot in the center of a huge, ghostly snow globe. Every direction you look, there are distant, icy bodies lazily orbiting the sun on random, tilted paths, no longer lined up with the orderly plane of the planets. So how many mines are we talking about? Astronomers estimate there could be on the order of 1 trillion icy objects out there, 1 kilometer wide or larger. Some estimates even go higher when you include smaller fragments. Picture a 3D cloud of trillions of frozen rocks and snowballs, roughly the size of mountains, spread across distances measured in light years. On average, neighboring objects might be separated by distances comparable to the gaps between planets. But at that scale, it's still a massive population. It's not dense like an asteroid belt in sci-fi movies, but statistically, it's an incredibly crowded reservoir of potential comets. Scientists think the Oort Cloud has structure too. There's an inner region, sometimes called the Hills Cloud, where the density of objects may be much higher, and an outer region where objects are more diffuse and more vulnerable to being nudged away by passing stars and the collective gravity of the galaxy. Over billions of years, the inner region may have been slowly resupplying the outer parts, keeping the overall cloud from dissolving completely. It's like a deep freezer with shelves inside. Most of the food is on the inner shelves, but a few items are perched farther out, ready to fall off when someone bumps the door. And here's where it really starts to feel like a cosmic minefield instead of just a pretty mental picture. Those outer items on the edge of the shelf are the most vulnerable to being kicked into motion. A passing star doesn't have to come anywhere near the planets to cause trouble. It only has to swing close enough to gently tug on the orbits of those distant, weakly bound chunks of ice. Over millions of years, those tiny gravitational taps add up. One object's orbit gets stretched a little more, another gets tilted, and every so often, one gets just the right nudge to start falling inward toward the sun. On top of that, our entire solar system is bobbing up and down through the Milky Way's disk like a ship riding slow waves. As we move through slightly denser regions of gas and dark matter, the collective gravity of the galaxy itself can very subtly shuffle the deck of the Oort Cloud. It's not like a dramatic explosion. It's more like someone leaning on that big freezer door for a very long time. Eventually, a few of those edge-sitting ice balls lose their balance, slip off the shelf, and begin the long, cold plunge toward the inner solar system, where we finally notice them as comets blazing across our sky. And we do keep bumping the door. Our solar system doesn't sit still in space. It orbits the center of the Milky Way, passing through regions with different densities of stars and gas. From time to time, a nearby star glides relatively close by on a cosmic scale, or we move through a denser patch of the galactic environment. Those subtle gravitational tugs, plus the gentle but persistent force of the galaxy itself, can disturb the delicate orbits of Oort Cloud objects. One small nudge out there can translate into a huge change in the shape of an orbit, turning a quiet, distant ice ball into a comet on a death-defying dive toward the inner solar system. When that happens, the mine goes off, not as an explosion in the cloud, but as a long, drawn-out fireworks show when the comet finally approaches the sun. As it comes in, sunlight heats the icy surface. Frozen gases like water, carbon dioxide, and methane start to sublimate, blasting jets of vapor and dust off the nucleus. That dust and gas form the glowing coma and tail we see from Earth. Long-period comets like Hale-Bopp or C/1995-01, which took thousands of years to swing around the sun, are prime suspects for having originated in the Oort Cloud. Not all of these visitors are friendly background scenery. A large comet has enough energy to seriously mess up a planet's surface if it hits. Some impact events in Earth's history, mass extinctions, global climate disruptions, could have been triggered by big cosmic projectiles, whether from the inner solar system or from this outer reservoir. That's why it's fair to say we exist inside a kind of cosmic minefield. We are sitting deep in the gravitational well of the sun, but far above us in all directions is a cloud of dormant, icy missiles that can be jostled into our path. But the Oort Cloud isn't just a threat. It might also have been a delivery service. Comets are rich in water and organic molecules. Some scientists think that comets bombarding the young Earth could have brought a significant portion of our water and some of the raw chemical ingredients necessary for life. So the same minefield that can occasionally throw a catastrophic impact our way might also have played a part in seeding our planet with the materials to become habitable in the first place. It's a cosmic double edge. Danger and potential life support, packaged in the same frozen shells. How did astronomers figure all this out without ever seeing the cloud directly? One key clue came from studying the orbits of long-period comets. When you calculate how stretched out those orbits are, you find that the farthest points, where they turn around and head back toward the sun, tend to cluster around tens of thousands of astronomical units away. That suggests they spend most of their time in a distant, roughly spherical reservoir before occasionally being perturbed inward. The pattern of these orbits is hard to explain if comets were born right where we see them now, but it makes sense if they've fallen in from a huge outer halo. Another clue is the distribution of directions they come from. If comets were mainly scattered from a flat, disk-like region close to the planetary plane, you'd expect their arrival directions to line up roughly with that plane. But instead, the long-period comets we observe come in from all directions, as if they're raining down from a spherical shell around the solar system. It's like watching raindrops hit your car from every angle and inferring that the storm cloud above you is a big, puffy mass rather than a flat sheet. Zooming back to our minefield idea, it's important to realize that most of the time, those mines just sit there, orbiting peacefully, never coming close to the inner solar system. The timescales are enormous. An object in the far outer Oort Cloud might take millions of years to complete a single lazy orbit around the sun. But the galaxy doesn't care about our sense of time. Over billions of years, enough small nudges accumulate that some fraction of objects inevitably gets kicked into long, looping trajectories that intersect the inner regions where the planets live. From the perspective of a human lifetime, that might sound comforting. Most Oort Cloud comets that will ever hit Earth did so long before we were around, and most that ever will do so long after we're gone. But from the perspective of civilization or of planetary defense, it's a reminder that space isn't empty. Our cozy inner solar system neighborhood is nested inside a much larger structure we can't see, full of slow-moving, frozen remnants of planetary formation that can occasionally dive in and demand our attention. Here's another mind-bending twist. The Oort Cloud probably isn't made only of objects that were born here. As the early sun and its planets were forming, there were likely other young stars and planetary systems forming nearby in the same cluster. Their gravity and ours interacted. Some of our early icy bodies might have been stolen by passing stars. Some of theirs might have been captured into our outer halo. So the Oort Cloud could be a kind of junkyard of not only our own leftovers, but also interstellar imports, foreign material quietly orbiting our sun for billions of years. And then there's the question you might be thinking already. Is the Oort Cloud the edge of the solar system? The answer is kind of, but not really. Dynamically, many scientists treat the outer Oort distances, tens of thousands of astronomical units away, as roughly where the sun's gravitational dominance fades and the galaxy takes over. But in another sense, the influence of the sun never truly drops to zero. If you enjoyed this trip to the edge of the solar system and want to explore more hidden structures, like the Kuiper Belt, rogue planets, and the real shape of our cosmic neighborhood, make sure to subscribe, tap the notification bell so you don't miss the next deep dive, and share this video with someone who still thinks space is mostly empty.